SpaceX Starship is considered humanity's best hope for landing on Mars in the near future. Its immense power and design give it the potential to not only transport astronauts, but also significant amounts of supplies to support a Martian mission. However, sending a spacecraft to Mars is one thing. Safely landing on the Martian surface presents one of the most complicated and perilous maneuvers in space travel. The journey's make-or-break moment revolves around the challenges of entry, descent, and landing EDL on Mars, where various factors come into play that many may not fully appreciate. To understand how the SpaceX Starship might land on Mars, we need to first comprehend how it gets there. In space travel, everything is constantly in motion, especially within a solar system where all planets orbit the Sun at varying velocities. Earth orbits the Sun at 30 kilometers per second, while Mars, being further from the Sun, orbits at 24 kilometers per second. Traveling through the solar system is primarily about adjusting velocity relative to the starting point. In technical terms, this is referred to as delta V, which describes a change in velocity. A spaceship must accelerate or decelerate its velocity to move between planets, rising out of the Earth's gravity well toward Mars by speeding up. Launching from Earth is challenging because of the substantial delta V required to escape Earth's atmosphere and gravitational pull. The Starship needs an incredible amount of thrust to overcome these forces, which is why the super heavy booster is essential during liftoff. After reaching low Earth orbit, the Starship needs to refuel before continuing to Mars. The journey to Mars requires almost the same delta V as escaping Earth, emphasizing the importance of power and fuel efficiency in space travel. While getting to Mars is a matter of acceleration, landing on the planet requires deceleration, and therein lies the challenge. The Starship in low Earth orbit is moving fast, and it must carefully manage fuel to ensure it has enough delta V to slow down and land on Mars. The forces of gravity and atmospheric drag, which made leaving Earth difficult, become allies in slowing the spacecraft for landing. However, there's a delicate balance. To avoid overshooting Mars, the Starship needs to decelerate and enter Mars' gravity well. During this phase, the spacecraft must conserve as much fuel as possible, as the Starship will need it for the critical landing burn when it gets closer to the surface. As the Starship approaches Mars, it must perform a complex series of maneuvers, utilizing aerodynamic drag and gravity to slow down further. Mars' atmosphere, though thin, still provides some resistance, which helps in reducing velocity. This approach involves dipping into the Martian atmosphere in a controlled manner to gradually shed speed. But eventually, the Starship will need to dive deep into the atmosphere, flipping upside down to increase aerodynamic drag during descent. The spacecraft's belly flop maneuver, which creates maximum drag, is a crucial part of reducing the Starship's velocity for landing. Unlike Earth, where parachutes can be used to slow descent, Mars' thin atmosphere makes this strategy ineffective. Instead, the Starship will rely entirely on its engines for the final landing phase. After creating as much drag as possible, the engines will reignite, flipping the spacecraft into a tail-first position. At this point, the remaining fuel will be used to execute a soft landing on the Martian surface. This landing sequence leaves no margin for error, meaning that every step must be flawlessly executed. Landing the Starship, a massive vehicle, on Mars is more difficult than landing smaller spacecraft. NASA has landed smaller, lighter rovers on Mars, which required much less fuel, and the SpaceX Starship is considered. In contrast, the Starship's larger size and need to carry supplies and humans make it a far greater challenge. The larger the spacecraft, the more fuel it requires, and SpaceX must find ways to increase the Starship's fuel efficiency. Future Starship iterations may feature larger fuel tanks and improved Raptor engines for higher delta V potential. There are long-term solutions being considered as well. For instance, an outpost or fuel depot on Mars' moon. Deimos, could allow for refueling before landing on Mars. This would provide a crucial safety margin, as landing a fully loaded Starship on Mars without any refueling is a monumental task. Refueling in the vicinity of Mars could significantly increase the chances of a successful landing. In conclusion, landing on Mars with a Starship is an enormously complex task. SpaceX faces incredible technical challenges in making this mission a reality, and failure is a real possibility during the development and testing phases. However, the ambition to reach Mars reflects humanity's long history of pushing boundaries and accomplishing the seemingly impossible. Landing the Starship on Mars represents not only a remarkable feat of engineering, but also a critical step in establishing a future where humans could live on another planet.